Alright, hello guys. Today we're going to be covering section 2.3, which is going to be calculating limits using the limit laws. And again, like what we've done recently is just, going over some limits, going an idea how we can, kind of guess what limits are. But we haven't gone over the precise methods of how we can actually find out what these limits are. How can we actually, calculate them? So in order for us to do that, we have to use a thing called the limit laws, which is basically just, some properties of limits that we can take advantage of that allows us to actually, calculate them. So the first things first, if we need some definitions, we want to show some laws, so we need some just arbitrary stuff. That way we can kind of write down laws. So the first thing is we need to let's suppose that, C is just a constant, just an arbitrary number, not anything specific. That's what we call it C. And we say the limits of two functions exist at the same point. In other words, we say the limit as x goes to a of f of x exists. And we can say that the limit as x goes to a of g of x also exists. So exists. This way we just have, two functions that are, that way we can kind of ask ourselves, what is the sum of the functions? What is the difference of the functions? What happens if we divide them or multiply them? And this comes in handy in trying to break down limits. All right, so then we have, in this case, a lot of limit laws that we can use. So I'm just going to start listing them off one by one. All right, so the first one is the limit as x goes to a of f of x plus g of x. So in this case, the sum of the functions is equal to the sums of the limits. So what that means is we have the limit as x goes to a of f of x, and then plus the limit as x goes to a of g of x. So what this means is we basically can distribute the limit over, the functions. In other words, the limit of the sum is equal to the sum of the limits. That's another way you can write that, or just say it. And then there's number two, which is going to be similarly defined, which would be the limit as x goes to a of f of x minus g of x. I think you guys can probably guess what this is equal to. Limit as x goes to a of f of x minus the limit as x goes to a of g of x. So in this case, the difference of the functions, the limit of the difference is equal to the difference of the limits. And, but that's kind of clear to see. If we just replace, in fact, these two are basically the same thing. Here you just let, g of x equal to negative g of x. Because one is just the negative of the other, but I wouldn't worry about that too much. So the third one is, let's just say with the limit as x goes to a, and then we have c times f of x. So this is just a constant being multiplied by a function is equal to the c times the limit as x goes to a of f of x. So basically what this means is if we could pull out the limit, we basically can pull out that constant. Let's see, for 4. So this one's going to be similar to 1, where we have, instead of the sum, we're going to have the product. So it would be the limit as x goes to a of f of x times g of x is equal to the limit as x goes to a of f of x times the limit as x goes to a of g of x. So in this case, the limit of the product is equal to the product of the limits. And likewise, how we can do the product, as we did, addition, we also have subtraction. As we have multiplication, we also have division. But with division, there's one more technicality we have to worry about. But, you'll kind of see how it makes sense. So limit as x goes to a of f of x divided by g of x. And as you guys can guess, it's going to be the limit as x goes to a of f of x divided by the limit as x goes to a of g of x. You shall note here that this is only true if the bottom piece isn't 0, otherwise it's ill-defined. So we say as if the limit as x goes to a of g of x does not equal to 0. If it's equal to anything else, then it's fine. So there's 5 of these so far. Basically what it means is the limits break up over sums and differences. You can pull out constants. And then limits also can break up over over like products and division. So just a quick example of how we can use this. So let's just say we know that the limit as x goes to 5 of f of x is equal to 10. And we have the limit as x goes to 5 of g of x is equal to 4. So then, if we know that, then we want to calculate some other limit. So let's just say we want to find the limit as x goes to 5 of 4 times f of x minus 5 times g of x. So again, here what we're going to do to evaluate this limit is just use the limit laws. So the first one we're going to do is 2, because here we have a difference of them. So this is equal to the limit as x goes to 5 of 4 times f of x minus the limit as x goes to 5 of 5 times g of x. And that will be equal to, and now we're going to use the third line, basically, well, the third law, I guess you could say, that allows us to pull out the constants. So this will be equal to 4 times the limit as x goes to 5 of f of x minus, and then here we're going to pull out the 5 times the limit as x goes to 5 of g of x. And again, we still want to evaluate this, but here we know the limit as x goes to 5 of f of x is equal to 10. Oops. And then we know this limit right here is equal to 4. So this is equal to 4 times 10 minus 5 times 4, which will be equal to 40 minus 20 is equal to 20. And that's our answer. So note that the only thing we did here is just, we use the limit laws. Every single line that we had was just using the limit law. So if we're going from here to here, we use 2. Going from this line to going from this line to the next line to here, we just use 3. Then here, all we did was plug in what we know. And note that every line that we did, there's a logical thing we did. We can say which limit law we used every single line, every single equality that we have. And this is how the idea of how we naturally, find what the values of limits are. It allows us a very natural way to find out what the limits are. And usually what it is it's a bunch of algebra. So one of the things that's going to be kind of important on the homeworks is knowing to do some algebraic tricks, which I'll make sure to go over some for you guys as I continue this. Okay, so there's not just 5 limit laws, there's a bit more than that. So let's keep going. So the first one's going to be, let's see, we still have the same setup as before. C is a constant, f of x and g of x have limits as x goes to a. So we're just going to keep on applying the same kind of assumptions as last time. So the limit as x goes to a of f of x, and this is going to be, to the nth power, is equal to the limit as x goes to a of f of x, and as you guys can probably guess, this will be to the n. In this case, n is a positive integer. And just in case you guys might not remember exactly what positive integer is, it's just of the form n equals like 1, 2, 3, 4, and so on. It's basically like you're counting numbers except for 0. And then 7 is going to be kind of similar to one of the previous ones we did. It's a limit as x goes to a of just c, as in just, in our case, our function could be a constant function, but our argument to the limit is just a constant. This is equal to just c. And we have 8. This is the limit as x goes to a of x is equal to a. So this right here is really important, because basically what this means is that, if we have just a function x, the way we can evaluate this value is just to plug in the limit. And then we can kind of extend that as like what we did with 6. If we raise everything to the nth power, we get the nth limit. So now we'll just write that down. So for 9, that will be the limit as x goes to a of x to the n is equal to a to the n. And that's kind of what we see when we combine 8 with 6, where we just get, into we get a to the n. In this case, n is still a positive integer. And then for 10, my bad. So we have the limit as x goes to a of, now it's going to be, instead of, we do like to the nth power, now we're going to do the nth root. So n x, so the nth root of x is equal to the nth root of the limit, a. And again, we have n is a positive integer. And there's another requirement that we have to have. We have to have a is greater than 0 if n is even. Because if the limit as x goes to a was -1 and we're doing the square root, then obviously it doesn't make any sense. Then likewise, how what we did here with x, we can replace it with f of x. So then we have the limit as x goes to a of the nth root of f of x is equal to the limit as x goes to a of f of x, and then you can write that as nth root. And note, just for you guys, one of the things I might do, just because I'm always pretty bad at drawing square roots or any of that kind of stuff, or maybe it's because it's something I forget to add while I'm writing it. I might also write limit as x goes to a of f of x, and then parentheses 1 over n. And note, the fact that I might switch between these pretty regularly, pretty often. So just kind of keep in mind what that means, and that these are actually the same thing. And again, in this case, n is also a positive integer and kind of has the same conditions as above. So using these limit laws, let's actually try to evaluate a limit. All right, so the first one will be the example. It's going to be, you want to evaluate the limit and we have the limit as x goes to -2 of x squared plus 2x squared minus 1 divided by 5 minus 3x. And so what I'm going to be doing right here is going to be very technical. I'm going to be applying every single limit law I can. That way we can actually, evaluate the limit. Sorry, I was a bit thirsty. I don't know if you guys hear me sipping on my Chick-fil-A drink. And note the way we're doing it here can be simplified, as we'll see. Well, not so simplified, but we don't have to be so tedious. So we're going to apply something that was kind of helpful, that, that we'll do something in the future that will make this kind of process easier. But in the meantime, we have to verify why these things are true. We have to go through every technical detail at first. Which I know seems annoying, but mathematics, if you want to be perfect at it, if you want to be good at it, you have to be tricky about the details. You have to worry about the details. So the first thing we shall do in evaluating this limit is we're going to appeal to this law right here. So now what we're going to do is, just break up the limit over the difference, or no, to break up the limit over the quotient. So this will be equal to the limit as x goes to -2 of x squared plus 2x squared minus 1 divided by the limit as x goes to -2 of 5 minus 3x. And this will be equal to, and this is where I'm going to need a lot of space. Oh wait, I'm dumb. Okay, this should be a cubed. I was wondering. Alright, sorry guys. So then what we're going to do is the limit as x goes to -2. And now what we're going to do is break it up, over every single, break it over the sums. And one of the things I'm going to do is I'm going to go ahead and pull out the 2 and pull out the 3 when I write them. That way I don't have to, that way I can kind of do 2 steps at once. And note that whenever I did the previous examples above, I did everything step by step. I only applied one limit law at a time, but if you kind of know what you're doing, you can do kind of like multiple steps at once. Alright, so what this means is the limit as x goes to -2 is equal, at the top, the numerator is going to be equal to the limit as x goes to -2 of x cubed plus 2 times the limit as x goes to -2 of x squared minus the limit as x goes to -2 of 1. And that's going to be all divided by the limit as x goes to -2 of 5 minus 3 times the limit as x goes to -2 of x. And now we can appeal to all the laws we had before, which in this case is going to be, these laws are here. They basically just tell us we can plug it in, and if it's a constant, then it's just equal to the constant. So again, for this one, for x cubed, x squared, and for x, all you have to do is just plug it in. So we get is -2 cubed plus 2 times -2 squared minus, and again for constants, all we have to do is just, leave it as a constant. It's just equal to the argument, b minus 1, divided by 5 minus 3 times -2. And when we simplify that, we just get, this will be -8. -8, this will again will be just +8 plus 8 minus 1 over just 5 plus 6 to equal -1 over 11. And that's our final answer. So again, it might be kind of tedious to write all this stuff out, to write all the steps, to write, break out the limits. But there's a thing that we can do that kind of gives this idea. If you want to try to search something fun, if you just plug in x minus 2, x to the, if you call this function like, if you call like this argument like g of x or whatever, we should note that if you just plug in -2 right here, as we kind of see as, with all the things we're doing here, like, in this case, for 9 and 10, the limit law is so the limit law is like 8, 9, 10, or all we did was really just plug in the limit. And this kind of idea, we can extend that to like, higher, like not higher things, but more complicated kind of things, like more complicated algebraic expressions. Man, sorry I keep on tripping up over my words. It's easier to write in math than it is to say it. But basically, well, if we just plug in -2 right here, we should note that we basically get the same thing as right here, which is going to equal to like our end result. And that's kind of the idea behind the next thing we're going to go over, which is going to call the direct substitution property. All right. So the direct substitution property is just, a property of nice functions. So nice functions meaning, we can kind of write them as like polynomials or like rational functions. And note that if I ever use the word nice to describe something, it just means, if I say a function is nice, it just means it kind of fits what we consider it to be nice. So in this case, a nice function would be like a limit. The limit exists, and maybe we could just plug the value in. But to specify what I'm talking about right here is they say if f is a polynomial, if I can spell it right, in this case, this will be able to form like, ax to the n plus, like you say an x to the n plus an minus 1 x to the n minus 1 all the way up to like a1 x1 plus a0. This is just a generic form of writing a polynomial, which basically just means any polynomial. Or a rational function. And again, a rational function is basically just a polynomial or a polynomial. So an example of just what this might look like would just be like, it is basically the previous example. It would be like x cubed plus 2x squared minus 1 over 5 minus 3x. That would be an example of a rational function. Then we have, let's just say, and one more thing we have to specify is say if a is in the domain of f, then the property that we want is the limit as x goes to a of f of x is equal to f of a. And this is the main idea of what I was just saying, is that if you have a nice enough function, in this case, f is a polynomial or a rational function, all we can do is just plug in a, and that's sufficient. So now let's do an example. So our example that we're going to be doing is we want to evaluate the limit as x goes to 3 of 9 minus x squared over x minus 3. Whoops. Oh, is it raining outside? Sorry guys, I heard noise. I'm like, it sounds like it's raining. I'm like, oh, worried about my plants. Okay. If you take a little note of this real quick, I'm just telling you about the direct substitution property where a is in the domain of f of x. And here our a is equal to 3, but we should note that if this is our f of x, that we can't actually plug in 3. If we plug in 3, we just get 9 minus 3 squared divided by 3 minus 3, which is equal to 0 over 0. And I really want to specify, this is kind of important to go from 0 over 0, let me just write it into parentheses, is called an indeterminate form. So an indeterminate form is just a form that we cannot find the limit about. It means it has no information that can help us out, and we have to do more. Hence why it's called an indeterminate form, because it doesn't tell us what the limit is. And some of you might be asking, well, what is the limit? Actually, how can we even say there's a limit? There's a vertical asymptote at x equals 3. So this is where we have to do a bit more work. In this case, just a hint, if you get 0, 0, let me just write it down. If we get 0 divided by 0, this means do more work. Work could mean, algebraic manipulations. It could be using identities. It just means we need to change the function a little bit, that we can have it in a more easier, like, and like an easier form for us to work with. So how do we get around that? So let's just look at 9 minus x squared over x minus 3. And this is kind of the part where I'm telling you guys, where during the calculus proficiency exam, that it was kind of important to make sure you know the material well enough, because all the pre-calculus that all the college algebra that you guys know, are all going to be coming up when we do these limits. So in this case, we're going to appeal to the fact that 9 minus x squared, that is a difference of squares. So this is equal to 3 minus x over 3 plus x divided by x minus 3. And then this is the same thing as negative x minus 3 times, well, we can do 3 plus x divided by x minus 3. And all I did was pull out a negative from this term. And then what we noticed is that the x minus 3's will cancel, leaving us with negative 3 plus x. And one of the things we should know is that, what do these inequalities actually mean? So here, if we look on this side, we say x cannot equal 3. And when you go through these inequalities, we still say x can equal, negative 3. Well, not negative 3, but x still can equal 3. But what is one of the things we notice about this form right here? If we just forget that the fact as if we just forget that the fact that here we're saying negative 3 plus x is is equal to this, but if we just look at negative 3 plus x by itself as just in a function, then we say it's nice enough where we can actually just plug in 3. So let's just say if we did the limit as x goes to 3 of negative 3 plus x, that'll just be equal to the negative, that'll be equal to, it's just negative 3 plus 3 is equal to negative 6. And the reason why is because 3 plus x is just a polynomial, so we're allowed to just plug in 3. And that idea is how we're going to be using this. So even though that, if we look at these functions, if we look at these chain of inequalities, even though right here, we're still saying x can equal 3, but what is the thing about limits? Is that limits don't care what you actually equal to at that point. Limits only care as, what are you doing around that point? What are you tending to? And because of that, we can actually begin to use these inequalities. So we have the limit as x goes to 3 of 9 minus x squared over x minus 3. And again, this doesn't care about x equals to 3. Thus, again, this doesn't care about x equals to 3. The only reason we can't, use the fact that x equals 3 is because it's a rational function, but x is not in the domain of it. But we know that this function is equal to negative 3 minus, let me just write it out first. So this function, fudge. Sorry, guys. Okay. So we know is that this function, does not define at 3, but it's a quotient. It is it's a rational function. So the idea is we want to use the direct substitution property. We should be able just to plug it in. But the fact is that it's not in the domain. And when we do plug in 3, we actually get 0 over 0, which is an indeterminate form. So that tells us we need to do a bit more work. In this case, this would be our work. And what we found out, that this function is equal to negative 3 plus x for everywhere when x is not equal to 3. But if we just look at 3 plus x by itself, as what we did right here, just considering it as an actual function, we get that this happens. So in this case, we're allowed to evaluate this limit as equal to just negative 6, as what we did above. And that actually gives us what this limit is equal to. So it's a way to like talk about problems in terms of something else. In this case, this limit right here wasn't nice enough, so what we had to do was reduce it to something nicer, and then you evaluated that limit. And that's a lot of times you might have to, and that's something you might see a lot when you have to do these limits, is that if you get 0 over 0, then you have to do some algebra to get to something nicer. So I'm just going to keep on chugging with another example. That way it's not a bit clear what I mean. So example. So now we want to find the limit as, well, we want to evaluate the limit as u goes to 2 of the square root of 4u plus 1 minus 3 all over u minus 2. And again, this isn't like a polynomial so much. Sorry about the email. This isn't a polynomial, and even if we wanted to plug in 2, if we plug in 2, what we get is just 4 times 2 plus 1 minus 3 over 2 minus 2, which is just equal to the square root of 8 plus 1 minus 3 over 0. And again, this is just equal to square root of 9 minus 3 over 0 is equal to 0. Just got a phone call. Sorry about that, guys. But again, we just get 0 over 0. And again, another indeterminate form. So again, so 0 over 0, what this means is do more work. That's how I always imagine it. That's how I write it down. I get 0 over 0. I say balls, or wait, that's not appropriate. I say flip, and I'm like, crap, now I gotta do more work. So now the question is, and this is where your pre-calculus comes in. This is why having a good solid foundation comes in, is how the heck do you simplify that? How the heck do you write that in a nicer way? And this is where you got to learn some algebra. So let me try to write it in black. So now we're just going to forget the limit real quick, and we're just going to work with the actual function. So we have the square root of 4u plus 1 minus 3 over u minus 2. So what we're going to do here is we're going to multiply by something called a conjugate. So the conjugate typically is we talk about in terms of complex numbers, but we want to talk about conjugate with respect to this. And this is typically what happens when you have like a square root minus something without a square root. So the conjugate, in this case, we would keep the first thing the same. So 4u plus 1, then plus 3. And we divide that by a square root of 4u plus 1 plus 3. Again, because we can only multiply by 1, so these things have to equal. And again, so the conjugate of this would be this right here, but instead of the minus 3, you would change that into a plus 3. And the reason why is we're using the property of this is a minus b, and this will be a plus b, and therefore the top would be like a squared minus b squared. And that's basically what we're doing, is we're trying to use, the difference of squares. So now we just have to, simplify, plug things in. And what we're going to get is, like I said, here was a squared minus b squared. So what we get is 4u plus 1, because that's going to be a squared, minus b squared, where b is equal to 3. So we just get 9, divided by u minus 2 times square root of 4u plus 1 plus 3. And now we just have to keep on simplifying. All right, it's definitely raining, so you guys hear the rain. I apologize. I like rain sounds, so hopefully you guys do too. All right, so let's keep on simplifying. So we have 4u plus 1 minus 9, which is the same thing as just 4u plus 8, divided by u minus 2 over the square root of 4u plus 1 plus 3. And then if I take out a 4 up top, that's going to be 4 times u plus 2. Is that plus 2? Oh, crap. I'm dumb, guys. This is supposed to be negative 8. Because this is supposed to be a minus 2. All right. So we pull out a 4, we get 4 times u minus 2 divided by u minus 2, and then still have the square root of 4u plus 1 plus 3. And now what we see, the magic that we've been trying to do, is trying to get rid of that u minus 2 on the bottom, so these will cancel, leaving with just 4 divided by square root of 4u plus 1 plus 3. And we did all that work just to write it in this form. And now what we can do is appeal to the direct substitution property of just plugging in 2. So again, the original thing we were doing was finding this limit. And what we have now is the limit as u goes to 2 of, let's see, what was it? Square root of 4u plus 1 minus 3 over u minus 2. And again, we did all the algebra to show that it's equal to this. Is equal to the limit as u goes to 2 of 4 divided by square root of 4u plus 1 plus 3. And what this is equal to is just equal to, what happens whenever we plug in 2 to get 4 divided by 2, well, 4 times 2 plus 1 and plus 3, which will be equal to 4 divided by square root of 9 plus 3, which is equal to 4 over 6. And you can leave it like that. And you can simplify if you want. This is calculus. I'm studying your calculus. I want to see how well you do calculus. If you don't simplify, I do not care. I'm not Lori in that regards. So in this case, this is pretty nice. All we have to do is a bit of algebra, and it's surely, don't call me Shirley, but anyways, sometimes, how do we even know the algebra to do this? How do we even know how to multiply by the conjugate? Sometimes it's annoying, sometimes it's not easy to see what the algebra is, and a lot of that times that requires just a bit of work and a bit of knowledge on how to do these problems. So, but there's some cases where the limits are just not nice at all. Like sometimes we can't really do this algebra to get us a nice answer. Sometimes it's even if we do a bunch of algebra, maybe the answer is still not clear. So let's talk about like a different kind of situation. So what would happen if we have the case, let's just say we have the graph of a function. Let's call this point A, and just say it's right here, and then call this y value L. This will be x, and this will be y. And this is kind of the case we're going to be worrying about. So let's just say we have a function, call this function g of x, and then we're going to call this function that we want to evaluate, call this function f of x, and then one last function. And call this function h of x. So it's not necessarily clear from the graph. What we have is this chain of equalities. We have g of x is going to be less than or equal to f of x, which is going to be less than or equal to h of x. In this case, we want to try to find the limit as, x goes to a. But, f of x may not be nice, but let's just say the function that we want is squished between two other functions. You could say sandwich if you want. But the idea is h of x is between these two functions. Well, f of x between these two functions. And this is kind of idea of like sandwiching But this inequality right here is very important. And the fact that if you look at this point right here at A, they all equal to the same value. So just to make that a bit clearer, we have h of A is equal to L, f of A is equal to L, and then g of A is equal to L. So the question is, how can we relate this to limits? How can we relate the idea of squeezing a function between two other functions into limits? Oh my gosh. Hopefully she doesn't text me any more stuff. All right. And again, to kind of clarify what I'm talking about is we have the limit as x goes to A of g of x, which is equal to L, and we have the limit as x goes to A of h of x is equal to L. And since the fact that, f of x is going to be between g of x and h of x, that kind of squeezes us what the limit of f of x should be. So this implies that the limit as x goes to A of f of x is equal to L. And so right here is just kind of a bit of a natural setting. This is kind of just like, an idea of what's going on. But, let's try to make it a theorem. Let's, well, we're not trying to make it a theorem, but let's actually write it as a theorem. How can we use this idea in our understanding of limits, or how can we use them to actually evaluate limits? And this right here also has a very specific name, which is called the squeeze theorem. Squeeze theorem again, because we're just going to be squeezing two functions between another function. So if g of x is less than or equal to f of x, which is less than or equal to h of x, again, somewhere again to what we're doing above here, is that this graph right here basically gives us this inequality. So we're going to start with that inequality. And again, we don't need to specify that it's everywhere, just when x is near A. And again, A is going to be our limit point that we care about. And again, we don't necessarily care at A, not necessarily at A. Because even if, these functions have different values at A, the limits still have to exist and they still have to equal the same value. And then again, what the hypothesis was here is that they all meet up at the same point, and that gave us this. So that's also going to be part of our hypothesis for this theorem, is that we have the limit as x goes to A of g of x is equal to the limit as x goes to A of h of x, which is equal to L. And this is the same thing I said right here. But in this case, we're implying that the way I'm writing it is that it's clear that these things have to be equal. And then if this is true, if everything is held, if we have a function f of x being squeezed between two other functions, and that's what inequality means, squeezing, and we have that the limits of the two functions equal to the same value at some point A, then what we get is the limit as x goes to A of g of x, not g of x, of f of x is equal to L. So basically, this is an idea of like, maybe f of x isn't nice enough, but maybe we could squeeze it between two functions. Maybe in the kind of cases you would see this is true, this would be like, maybe f of x isn't nice enough. Again, nice enough meaning we could plug it in, isn't nice enough, but can be squeezed between two, nice functions. And again, nice just means we can actually do something algebra with it. There's like an easy way to find out what the limits are. So an example of what I mean by this, or an example where we can use the squeeze theorem is, is going to be in this case right here. So let's just say we want to evaluate the limit as x goes to 0. We have 3x squared sine of 1 divided by x. So one of the things we should notice here is that, if we look at the limit as x goes to 0 of, 3 of x squared, that limit is nice. It's actually equal to 0. But if we do the limit as, x, if we look at the limit as x goes to 0 of sine of 1 over x, this does not exist. And you can see that, like we kind of did an example in the last homework and why that's not true. But there's something that we can use about sines that we can actually do that. Well, we can actually evaluate this limit. So despite the fact, sine of 1 over x is very nasty, and we don't, it's kind of hard to find the limit of it, we know some nice, you can use some of the nice properties of sine of x. So one of the things that, you have to remember from trig is that any sine function can be squeezed between -1 and 1. So what I'm saying is, or what I mean is that we have this inequality. We have -1 is less than or equal to sine of 1 over x, less than or equal to 1. And this is one of those things you'll have to remember from just like trig. Another way of seeing that would just be like, instead of saying, 1 over x, we have theta. So this also works with cosines or sines, is that if we have any like sine function or cosine function, we always want to try to bound it between -1 and 1. But let's actually use that now. So we know that sine of 1 over x is going to be between -1 and 1. And we know that that 3x squared is always going to be greater than or equal to 0. So what we're going to do is multiply this inequality by 3x squared. And we have to specify that 3x squared is greater than or equal to 0, because if we multiply by something that could be negative, then that changes what the values could be. Then that would, flip the sign of the inequality, and you would have to be more careful of that. So now we're going to take 3x squared and multiply it by -1, times this inequality, and what we're going to get is -3x squared less than or equal to 3x squared times sine of 1 over x less than or equal to 3x squared. All right. So again, what we have right here is actually what we have inside the limit. So now we can try to appeal to the squeeze theorem. So now again, to use the squeeze theorem is we have to verify all the hypotheses. And that's one of the things about using a theorem. If you want to use a theorem, you have to make sure all the conditions are true. So again, this chain of inequalities is true. This would be our g of x less than or equal to our f of x less than or equal to our h of x. And then the last thing we need to show is that the limits of g of x and h of x as they go to the same value are the same. Or in this case, just specifying the part of the theorem that we're using is this case. So then we note that the limit as x goes to 0 of -3x squared is equal to 0. That's also equal to the limit as x goes to 0 of 3x squared. So in this case, they have the same limit, and therefore by squeeze theorem, and by the squeeze theorem, we have the limit as x goes to 0 of 3x squared times sine of 1 over x is also equal to 0. And again, what this problem is doing is basically just saying, all right, this thing is right here is messy, and the reason why it's messy is because of this. But sine of x is less than or equal to 1, and then, that's weird, alright. I got all the way up to the top of the page. But what this is saying is that because sine of 1 over x is between 1 and negative 1, then all we have to do is multiply by 3x squared, and then evaluate the limits. And because the limits are the same, which is a very important part of the squeeze theorem, then we can actually get the limit of the actual function that we want. All right. And I think that's it for the last section. I think this is it for just this section right here. And again, the important part is just kind of knowing what the squeeze theorem is, the idea of just squeezing a function between two other functions and making sure they have the same limit. If they don't have the same limit, you can't apply the squeeze theorem. And then remembering all your limit laws. So making sure you remember like just the natural properties of limits. And then, how we use them. Basically the idea is, if they're nice enough, we can plug it in. But if they're not nice enough, if we get like 0 divided by 0, this means we just have to do a bit more work. But that usually just means we have to simplify what we have. We have to try to write this in a way that makes sense, or not necessarily in a way that makes sense. But we try to write it in a nicer way. We can actually use the direct substitution property, where we can actually plug things in. And that's what I think it is on homework, where you have to just do a lot of work. And so yeah, that's it for this section. What I'm going to do real quick is just go over a bit of algebra terms for you guys, just a bit of algebra to kind of help you do a problem. So I'm just going to do just a quick example real quick, because I was looking through the homework and I noticed there might have been a few things that if you haven't seen the tricks for it, you may not know how to do it. So just like, for example, we have 1 minus t divided by 1 what the heck? I love when that happens. Okay, so we have 1 minus t divided by 1 minus square root of t. And again, what we want to do, if you want to say like the limit as like t goes to 1, clearly you get 0 divided by 0, which is in determinate form. So we need to find a way to like write that nicer. So the way we can do that is the limit as t goes to 1 of 1 minus t divided by 1 minus square root of t times. Now what we're going to do is try to get rid of the denominator. Try to get rid of that fraction, so we multiply by the conjugate. So it'll be 1 plus square root of t, and then 1 plus square root of t. Again, this is of the form like a minus b and a plus b. And the reason why is so we get the limit as t goes to 1 will be equal to 1 minus t times 1 plus square root of t. And then the whole reason why we're doing that is because this will be equal to, the bottom will be equal to a squared minus b squared, just to be equal to 1 minus t. And that's what we get for the limit is the limit as t goes to 1. We'll have that the 1 minus t's will cancel, we're leaving just 1 plus square root of t. And now 1 plus square root of t is nice enough where we can actually plug in 1. Just get 1 plus 1, which is equal to 2. And then there's another problem that I just want to kind of show you guys how to do. Is that one of the things you could do with limits is that limits are actually like numbers. So we could treat them like numbers. So we can multiply and divide by limits. We can add them if we wanted to. But just a quick example of what I mean, because I know this is on homework. So the limit as the x goes to, let's just say 1 of f of x minus 8 over x minus 1. And we say this is equal to 7, and we want to find the limit as x goes to 1 of f of x. So the way we do this is by, we do the limit as x goes to 1 of f of x minus 8 over x minus 1. We're going to multiply that by the limit as x goes to 1 times, let's see, x minus 1. And again, as you guys can kind of see, I'm kind of like, doing some algebraic manipulations to kind of get things nicer. So this limit right here is equal to 7, and this limit right here is equal to 0. So just a quick side note of like, what this is equal to is equal to 7 times, this limit will be x as x goes to 1 of x minus 1. And then, this is a polynomial, we could just plug in 1, so we just get 1 minus 1 is equal to 0. So this right here will be equal to 0. So just keep that in mind. And now let's actually, this is kind of like the backwards direction, I guess you could say. But now let's actually work with this side. So the limit as x goes to 1. And now the fact that we can use one of the properties is that, the product of the limits is equal to the limit of the products. So the fact that both of these limits exist, which is why I multiplied by this to begin with, is so we can actually combine them. So then we get the limit as f of x minus 8 over x minus 1, which will be this piece right here, then times x minus 1, which is this piece right here, will be equal to, and then the x minus 1s will cancel, leaving you the limit as x goes to 1 of f of x minus 8. And again, these are all inequalities right here, so this is equal to 0. Thus what we get is if we use, again, more limit laws, we get the limit as x goes to 1 of f of x minus the limit as x goes to 1 of 8 is equal to 0. We just move this to the other side. And the fact that the limit of a constant is equal to the constant basically just implies that the limit as x goes to 1 of f of x is equal to 8. So let me just kind of be mindful of what's going on again. Is that here what we did was we had this limit right here, but we want to get rid of this x minus 1 on the bottom. So what we can do is, multiply it out. We'll multiply the limit as x goes to 1 of x minus 1. And then we know that this is equal to 7 times 0, which is equal to 0. But then the reason why we multiply by this x minus 1 is so we can use the fact that we can write it as the limit of the product. And when we do the product, the x minus 1s will cancel. And that will just leave us of f of x minus 8 is equal to the limit as x goes to 1 of f of x minus 8 is equal to 0. Again, because this is just a chain of equalities, everything is equal to each other. And then we just do some limit laws on this. So we just use the fact that the limit of the difference is equal to the differences of the limits. Again, this is just previous laws that we learned. And then we know that this right here is equal to 8. So we just get negative 8 right here is equal to 0. Then we can just add 8 to both sides. And that's how we get our final conclusion. All right, so again, this stuff isn't so bad. If you have any questions, feel free to ask. I tried to look through the tricks that you guys had to use for this, just in case there wasn't anything too obvious. There was another problem I saw in the homework that was the limit as f of x divided by x squared, x goes to 0 is equal to 0, and they wanted to find the limit as limit as x goes to 0 of f of x divided by x. You want to figure out what this is, but this is right here is equal to the limit as x goes to 0 of f of x over x squared times the limit as x goes to 0 of x. And basically just use the same idea as before. This will equal to the limit as x goes to 0 of f of x over x squared times x. And that's kind of the idea of some of the other homeworks and assignments, is that sometimes you have to realize that limits are just numbers, so you're allowed to multiply them. You're allowed to multiply them, you're allowed to add them to the other side or subtract or any of that kind of stuff. Alright, I think that's all I had though. Thank you for watching. Like, comment, and subscribe.